Physics students, good afternoon. Mr. Fugit here. In our video today, we're going to be looking at a few of the problems on the review for test number 6. Specifically, the problems that we look at here are going to cover over the last parts of Unit 7 on heat transfer rates. So here we will be looking at the first two problems on the review for test 6. We'll not have the problems posted up here, so we have space to do our work. But if you would like a copy of the problems, there are hard copies available in class, as well as copies on Canvas, along with the key. So here we'll begin by looking at problem number 1 on the review for test 6. I'll read it for us and then we'll jump in. Our problem statement says this: I place an electric blanket at 30 degrees Celsius on my cold bed, about 10 degrees Celsius, on top of a thin sheet to warm it up before I go to sleep. If the blanket is 2 meters by 1.5 meters on the bed, and the sheet is 1 centimeter thick with a thermal conductivity of 0.04 watts per meter degree Celsius, how many joules of heat does the bed absorb in the first second I place the blanket on it? So here we're looking for joules of heat per time, which means we're probably going to be looking at a heat transfer rate. So as we've talked about before, conditions like this, where objects are in contact, the way that we calculate our heat transfer rate can be expressed this way: as a product of the thermal conductivity, the contact area, the difference in temperature of our two areas, as well as an inverse relationship to the length of our material, or the thickness of our material. So here, we'll take some of the values that were given and see if we can find our heat transfer rate. So H is equal to our conductivity, which we're told is 0.04 watts per meter degree Celsius. The area of our shape looks like a square, 2 meters by 1.5 meters. So we'll multiply those dimensions to get our total area. Delta T, our temperature difference. So we had a warm blanket that was 30 degrees Celsius, the cold bed which was 10 degrees Celsius. So the difference there would be 20. And divided by the thickness of our object here, 1 centimeter, or 0.01 meters. So let's see if we can use our equation to find what we're looking for. Thermal conductivity of 0.04 multiplied by 2 multiplied by 1.5 multiplied by 20 divided by 0.01, and we get a heat transfer rate of 240. So we have the watts, meters in the denominator, 2 meters, so meters squared, degrees Celsius, that would cancel out, divided by meters again. Really, all in all, we're going to get all of the units here to cancel out except for watts, and a watt can also be written as a joule per second. So this would be how we could use our heat transfer rate equation to find how much energy we lose, or how much energy the bed absorbs in the first second the blanket is placed on it. So hopefully this gets us going with just a very basic application of our heat transfer rate equation. We'll move on now to question number 2. Question number 2 says this: a window made of glass with a thermal conductivity of 0.96 allows heat to move through the window at a rate of 6,200 joules per second. The temperature on the outside of the window is 5 degrees Celsius, and the interior temperature is 30 degrees Celsius. Assuming the window is a square with dimensions of 2 meters by 1.5 meter, determine the thickness of the window in centimeters. So here we're looking at question number 2. And then the same idea using our heat transfer rate equation, but now we're trying to find a different variable, the thickness. So we have our equation. The heat transfer rate is a product of the thermal conductivity multiplied by the contact area and the temperature difference divided by the length or thickness. Now, if you prefer to put the numbers into the equation first and then solve, that's one way you can do this. I personally like to rearrange the variables first, just so I don't have to work with all the numbers yet. So, if I want to get the L variable, the length or thickness of the material by itself, it begins in the denominator of our equation, which means I need to multiply that value up to the numerator. So L divided by L, those would cancel out, and I would have something like L multiplied by H on the left side of my equation, and the right side would look very similar in the numerator. I didn't really do anything to the numerator. Now I would divide by H on both sides of my equation. These H's over here on the left would cancel out, and now I would have just L remaining. So, might need to redraw this. There we go. So now we have an equation that is set up to just give us the variable we need, the length or thickness of the window. So let's plug in what we do know. The length or thickness, we need the thermal conductivity, we're told is 0.96 watts per meter degree Celsius. The area, we can use the dimensions of the window, 2 meters by 1.5 meter. 1.5. And then the difference in temperatures between the warm area and the cold area. We have an outside temperature of 5 degrees Celsius, an inside temperature of 30. Difference there would be 25. Divided by our heat transfer rate, which is 6,200 joules per second. I'm going to write that as watts, just so I can show that those units will cancel out. So now let's see if we can use our equation to find what we're looking for. Let's go our conductivity, 0.96, multiplied by the dimensions of our window, 2 meters by 1.5 meters, 25 degrees Celsius, divided by 6,200. I'm going to get a reasonably small number here, but remember that is going to be a length in standard units, which would be meters, 0.0116 meters. So if I convert that to centimeters by multiplying by 100, I would get 1.16 centimeters. So about a centimeter, which is roughly about half of an inch, which seems pretty reasonable for the thickness of a window. So here are the first two problems on the review. We're using our heat transfer rate equation to analyze the energy moving through a material. Question 1, we're looking at a kind of a warm blanket, an electric blanket. And in question 2, we're looking at something a bit more traditional like a window. So hopefully this gets us just some good practice on using and applying our heat transfer rate equation. If there's any things that you have questions on, make sure to check Canvas for keys and other resources. And as always, you're welcome to direct questions to me. Best of luck.